So lesson four, it's on a very famous problem called the traveling salesman problem, which uh, about every 1 or 2 years, somebody says they found a better solution to. It actually just happened last month that they released yet another improved solution to the traveling salesman. Um, but what we're really focusing on here is a concept called a heuristic and dealing with what are called undecidable problems. Remember, algorithms are things that are finite sets of instructions to perform a task, ideally to solve a problem. However, they may take an unreasonable amount of time. So if an algorithm takes an unreasonable amount of time, we may settle for what's called a heuristic instead of an algorithm. And a heuristic provides a good enough solution when the actual solution is impractical or impossible. And those are the two possibilities. Impractical because it takes an unreasonable time, even though we know the algorithm would work, or impossible because there is no algorithm that could solve the problem. And those would be what we would call an undecidable problem in that case. So uh, we spent the last lesson talking about reasonable versus unreasonable. Remember, a reasonable algorithm is one that is linear or polynomial or like the binary search logarithmic, whereas unreasonable would be exponential or I had briefly mentioned factorial. So we're going to look at the traveling salesman problem. Having a piece of scrap paper is a good idea for this, again, to kind of just sketch out things that are happening as we do this. And the basic idea of it is you have your house and you want to visit other houses. So we're going to start with just 3 other houses. So you have to start at your house. You can only visit each house once, and you have to end at your own house. And come up with an algorithm that is the most efficient way of hitting all 4 houses, ending where I started, and not visiting not visiting any house more than once. So there are different paths to take. You could go around in a circle, starting at the original. Come on. And I wanted the laser pointer. Starting at your house, go to your next door neighbor, then to their next door neighbor, then to their next door neighbor, back to yours. Or you could go to your next door neighbor, then diagonally to the house across from them, then their neighbor, then diagonally back to you. Or from your house to next door neighbor, to diagonally to next door neighbor, back diagonally. There are different ways of doing this. So which one would make you decide that's the best path? And distance is the easiest way to do this. So you would want the one that takes the least distance. Well, our first example took a total distance of 4. Our second took a total distance of 6. I have some mathematical quibbles with saying these are distances of 2, but the important thing is they're longer than 1. And this also took a total distance of 4. So what happens now if we have a lot more places? How would we determine the best path? And this is what's called the traveling salesman problem. For every new place you visit, the number of options for possible paths increases factorially. So remember, factorially is I'm taking an integer times every integer smaller than it. So if I have 1 house to visit, there's only 1 path. 2 houses, there are only 2 paths. To that second house and back to my first. 3, well, 3 factorial is 6. 4 factorial is 24. 5 factorial is 120. 6 factorial is 720. By the time I get to 10 houses, I'm at almost 4 million different paths to check for the best path. So remember, factorial, it looks like an exclamation mark, but it just means that I'm multiplying that integer times every integer smaller than it down to 1. So this is an optimization problem. It can be solved with an algorithm, which checks every option, but it takes an unreasonable amount of time. because remember, because it's factorial. Remember, exponential and factorial are unreasonable. The algorithm works, it just takes too many steps. So this is where the idea of heuristic comes in. Can we come up with a good enough solution in the traveling salesman case because the algorithm we have works but is unreasonable, it's impractical. So you can actually try this out. If you go to level 2 of Unit 6, Lesson 4 on Code Studio, they have the traveling salesman problem set up, and you can play with it. Try it. It shows the distances connecting the house you're on to the other houses, and then you can go ahead and try different paths and see, can you come up with a heuristic that will always find the best path? Or not always, but usually find the best path. So keep in mind, this is not an algorithm because the algorithm would always find the best path. And we've established that that's just too many things to check for that to work. The heuristic will find a good enough short path. So it may not be shortest, but it's going to be short enough. And kind of do it a couple of times, record your answers, and see what you come up with. And then think about, what was your heuristic? Did you, as you were going through the different ones, did you change it any? And make sure you can explain your heuristic, because like an algorithm can be explained because it's a finite series of steps, you should be able to explain your heuristic while at the same time explaining it's going to give a good enough solution to our problem. So an example of heuristic is, when I go from one node to the next, always pick the next one based on the shortest distance from my present node. Okay. So the traveling salesman is an optimization problem, meaning we're trying to find the best path. It's an unreasonable one because the algorithm works but takes too much time. It's an unreasonable amount of time because it's a factorial. So we need a heuristic to come up with a good enough solution for it. So then there are things that are undecidable. The traveling salesman problem is not undecidable. It's unreasonable. Undecidable is something that an algorithm cannot come up with a solution to. It's not that it takes too long, it's impossible to do. So the next video in OneNote has a really good explanation of what's called the halting problem. The halting problem was explained first by Alan Turing, one of the original designers of modern computers and computing architecture and design. Explained it as a problem of that a computer could never have an algorithm to solve. So it would be undecidable, not unreasonable. Traveling salesperson, algorithm works, but it's unreasonable because it's factorial and takes too long. Whereas the halting problem is undecidable because there is no algorithm that will work for it. So the halting problem is what we call undecidable.